Hello everyone, and welcome to a video called Multiple Representations of Uniformly Accelerated Motion. Say that 5 times fast. So, we're going to use here as our paradigm the cart moving down the incline, as we're still working on here. And we graphed the position as a function of time, right? Position, one-dimensional position, and we got a parabola. So, let's talk about the slope of this graph. Now, first of all, it's a curve, so the slope of this graph isn't constant. In this case, is it increasing or decreasing? Well, let's take a look at a couple of tangent lines. Here's a tangent line early on. Here's a tangent line a little later. Look at the slope of those tangent lines. They are increasing. Also, these tangent lines are positive. And as we've defined several times, the slope of a position time graph is the velocity. So, by analyzing this graph of position versus time, we can see that we should have an increasing positive velocity. Well, when we did the lab extension, we of course got that kind of graph. We got a graph that looked like this. Notice that it is increasing. Zero velocity is right on the time axis. Right? So this is getting further away from the time axis, therefore it's increasing. It's a positive velocity because it's above the time axis. And so this is an increasing positive velocity. We'll see different cases of this in the activity you're going to do tomorrow. Let's look at the slope of this, though. The slope of this velocity time graph is neither increasing nor decreasing. It's a linear graph, so the slope is constant. It is, however, in this case, a positive slope. And as we determined in the lab extension, post-lab, the slope of a velocity time graph is the acceleration. So, by looking at this velocity time graph, we can tell we have a constant positive acceleration. Well, there is no reason to restrict ourselves to only position versus time and velocity versus time graphs. We could also make an acceleration versus time graph. We know the acceleration is constant and positive, so what would that look like on a graph of acceleration versus time? Well, first of all, if something is constant, its graph is horizontal. That means that at any time it's the same value. And to make it positive, it must be above the time axis. So see if you can wrap your brain around these 3 graphs. We're going to do a whole activity tomorrow where we're going to look at different situations of carts moving up and down inclines and see if we can begin to predict what these graphs look like and to interpret what they tell us about the motion. Now, I promised that this was multiple representations of uniformly accelerated motion. So, let's do a different representation. Let's do a motion map for the cart moving down the incline. You'll notice, first of all, that I've rotated the position reference line. It's position reference line. It's got an X on it, right? I've rotated it to be parallel to the motion because that way the motion is one-dimensional. We don't want to say that this thing is moving horizontally and vertically. We just want to say it's moving up or down the incline. One-dimensional motion. Now, if you remember, motion maps have dots. And those dots represent the position of the ball or the cart at equal intervals of time. So where does the cart start? Well, the cart starts at 0. And on a motion map, 0 is right above the tail of the arrow. Now, realize everything is tilted here, so I'm not going to put it straight up. I'm going to put it at an angle. Right? That's 0. 1 unit of time later, where is the cart? Well, it's down the incline a little bit. Now, not a lot, because it's not moving very fast to start out with, but it's moving down the incline a little. An equal unit of time later, where will the ball be? Well, it'll be further down the incline, but how much further compared to here? If you're thinking even further, you're right. Because what's happening here is the cart is speeding up. So that means in equal intervals of time, the cart will go farther and farther and farther. So looking at this, we can see here that this is a cart which is speeding up because the dots are getting further apart. Now, we also put arrows attached to those dots to represent the velocity of the ball. The direction of the arrow, which is pointing downhill, is the direction of the motion, and the size of the arrow represents how fast it's going, or its speed. Now, be a little careful here. This first dot is 0 time. For our cart moving down the incline, how fast was it moving at 0 time? That's right, it wasn't moving at 0 time. And so how big of a velocity arrow will it have? Indeed, it won't have one. The initial velocity is 0, so no velocity arrow on the first dot. Now, by the time we get to the second dot, now it's moving. So it'll have a velocity arrow pointing down the incline. And the third dot, it's moving, but remember, it's moving even faster. So we'll make a longer arrow, and then a longer arrow, and then a longer arrow, and then an even longer arrow. So by looking at the separation between the dots, you can tell it's speeding up. And by looking at the length of the velocity arrows, you can tell it's speeding up as it goes down the incline. The reason why there's no velocity arrow on the first dot is because it's starting from rest. This dot represents 0 time. Right? And 0 time, it's starting from rest. I know that's a little bit weird, but it's something we have to do. So if it's already moving at 0 time, maybe you've given it a push so it's already moving, well, now you would have an arrow on the first dot. Now, we're going to add a third thing to this motion map. We're going to add another arrow. And this one's going to represent the acceleration of the ball. Okay? Remember that acceleration is itself a vector, and therefore needs to be represented as an arrow. Now, what direction should that acceleration arrow point? Well, if you think back here, the acceleration was positive, and positive is down the incline. So our arrow is going to point down the incline. Now, I'm going to draw these acceleration arrows under the dots, not attached to the dots. Otherwise, they'd be overlapping, and it'd be hard to see them. Okay, so I'm going to put one under the dots. Now, should I have one on the first dot? Well, if you say no, think about what that would mean. If the object isn't moving and it isn't accelerating, what will it do? What will an object do with 0 velocity and 0 acceleration? That's right, it would just sit there. And when you let the cart go, did it just sit there? No, it accelerated down the incline. So it is accelerating at that point. And then it's accelerating the same amount there because it's a uniform acceleration, and the same amount there, and the same amount there, and the same amount there, and the same amount there. So you'll notice your acceleration arrows are all the same length. Now, if you're really drawing this well, if you take that arrow and add it to that arrow, you get this velocity. Then it accelerated this much, and you get that velocity. Then it accelerated that much, and you get that velocity. Now, I don't really expect you to be that perfect. Mine is because it's to scale, but that's the idea. Okay, the acceleration arrow is saying, hey, it's speeding up, so the velocity arrows have to get longer. So tomorrow we're going to do an activity where you're going to have carts going up and down the incline, and you're going to measure the position, the velocity, and the acceleration using a motion detector. So we don't have to get all many trials with the photo gates and things. We're going to use a motion detector, and you're going to have to try to predict what that motion is going to look like on the grass, and what the motion map is going to look like. So hopefully you remember some of the things we talked about here in this multiple representations of constant, uniform, accelerated motion.